Last video, we saw that the set of all x comma 0 such that x is a real number, union the set of all 0 comma y where y is a real number, is a subset of R2 that is not a vector space. However, notice that these two separate sets are both subspaces. Let us call these subspaces U1 and U2. So in general, we observe that if you have two subspaces U1 and U2, then U1 union U2 need not be a subspace. But as we are interested in vector spaces and thus our interest is on subspaces and not subsets, we will like to see if there exists a vector subspace W that contains U1 union U2. But of course, there exists one such subspace. What is the obvious subspace that contains U1 union U2? It is R2 itself. So what we would like to say is, can we find a smaller subspace that contains this? In fact, we would like to see what is the smallest subspace that contains U1 union U2. Now notice that if V comma W belongs to U1 union U2, then they also belong to W, which implies that V plus W should also belong to W, as W is a subspace. Now, if V and W both belong to U1, then V plus W belongs to U1 and hence belongs to W. On the other hand, if V and W both belong to U2, then again V plus W belongs to U2 and hence it belongs to W. Therefore, the interesting case is when U1 belongs to capital U1 and U2 belongs to capital U2. If this is the case, then as U1 and U2 both belong to U1 union U2, it belongs to W and thus the sum of these two should also belong to W. And this holds for every subspace that contains U1 union U2. Now, we will show that if you consider all such possible sums, that means you look at the set of all U1 plus U2, where U1 belongs to capital U1 and U2 belongs to capital U2, then this forms a vector subspace. And as this is a vector subspace, and any subspace that contains U1 union U2 should contain this, this would be the smallest subspace that contain U1 and U2. Let us now prove this claim. That is, if U1 and U2 are subspaces of V, then the set of all U1 plus U2 such that U1 belongs to U1 and U2 belongs to capital U2 is a subspace of V. To prove this, we have to first show that this set is closed under addition. That means we will take two elements, say U comma V in this set, which is of the form U1 plus U2 such that U1 belongs to capital U1 and U2 belongs to capital U2, which implies that U is of the form U1 plus U2, where U1 is in capital U1 and U2 is in capital U2, and V is of the form V1 plus V2, where V1 is in capital U1 and V2 is in capital V2. Therefore, U plus V is equal to U1 plus U2 plus V1 plus V2. But addition of vectors is associative. Therefore, we can rewrite this as U1 plus U2 plus V1 plus V2, which again by associativity is equal to U1 plus U2 plus V1 plus V2, which by commutativity is equal to U1 plus V1 plus U2 plus V2, which again by associativity is equal to u1 plus v1 plus u2 plus v2, which once more by associativity is equal to u1 plus v1 plus u2 plus v2. Now notice that u1 plus v1 belongs to capital U1 and u2 plus v2 belongs to capital U2. Therefore, it is of the form u1 plus u2 such that u1 belongs to u1 and u2 belongs to u2. Thus, this set is closed under addition. Now, let us try to prove that this set is closed under scalar multiplication. Therefore, we take an element u from this set and notice that this u is of the form u1 plus u2. Therefore, if you take c times u is equal to c times u1 plus u2. But as scalar multiplication distributes over addition, we get c times u1 plus c times u2. Once again, c times u1 belongs to capital U1 as U1 is a vector subspace, and c times u2 belongs to capital U2 as U2 is a vector subspace. Therefore, this sum c into u1 plus c into u2 belongs to the set that we are interested in. Thus, the set is closed under scalar multiplication. All that remains to show that this set contains the additive identity. Notice that the additive identity, which we will denote by 0, belongs to u1. Why? Because u1 is a subspace. Similarly, the additive identity belongs to u2 as u2 is a vector subspace. Thus, 0 plus 0 belongs to the set that we are interested in, namely the set u1 plus u2 such that u1 belongs to capital U1 and u2 belongs to capital U2. But notice that 0 plus 0 is equal to 0. Thus, 0 belongs to this set, that is, the additive identity belongs to this set. Thus, we have proved that this set is closed under addition, closed under scalar multiplication, and contains the additive identity, which means that this set is a vector subspace. As this set is very important and we will keep revisiting it, we will give it a name. We will call it sum of the two vector spaces u1 and u2. And as we are giving it the name sum, we will denote it by u1 plus u2. Now, as soon as we can add two subspaces u1 and u2, we can add 3 as well, because u1 plus u2 is a subspace, implies that we can add u1 plus u2 and u3. And observe that u1 plus u2 plus u3 is equal to u1 plus u2 plus u3. This is a simple application of the fact that addition is associative in a vector space. And I leave the proof of this fact as a homework. As the two subspaces are equal to each other, we can denote them by a common notation u1 plus u2 plus u3. And once we know how to add 3 subspaces, we can add 4. Why? Because the sum of these 3 subspaces is a subspace, and thus we can add one more to it. Once again, associativity implies that this is equal to u1 plus u2 plus u3 plus u4. It is also equal to u1 plus u2 plus u3 plus u4 and so on. So it doesn't matter in which order you do these sums. That's the whole point of associativity, and they are all same. As they are all same, we can denote them by a common notation u1 plus u2 plus u3 plus u4. Thus, we can inductively define the sum of n subspaces. However, you might have already realized that this procedure is very cumbersome. Therefore, it might be easier to prove inductively that u1 plus u2 plus etc. up to un is a set of all elements small u1, small u2 plus etc. up to un such that ui belongs to capital UI. And this is not very difficult to prove. And thus I leave it as a homework. Now let us revisit the example we started with. Let u1 be the set of all x, 0 such that x is a real number, and u2 be the set of all 0, y such that y is a real number. The question is, what is u1 plus u2? We know that u1 plus u2 is equal to the set of all u1 plus u2 such that u1 belongs to capital U1 and u2 belongs to capital U2. But notice that u1 is an element in R2 of the form x, 0 and u2 is an element of R2 of the form 0, y, where x belongs to R and y belongs to R. But notice that x, 0 plus 0, y is equal to x, y such that x belongs to R and y belongs to R. But this is equal to R2. Therefore, u1 plus u2, the sum of u1 and u2 is equal to R2. Thus, it was not very interesting. So, let us look at another example. This time, take u1 to be the set of all x, 0, 0, where x is a real number, which is a subspace of R3. And u2 to be 0, y, 0, where y is a real number. And once again, this is also a subspace of R3. Now we will see what is u1 plus u2. As before, it is easy to see that this is the set containing all x, y, 0 such that x and y are both real numbers. And this is a subspace of R3. Moreover, this u1 plus u2 is not equal to R3. Thus, we have managed to find a smaller subspace than R3 that contains u1 and u2. And thus, it's more interesting. Let us end this lecture with one more example. This time, you take two subspaces of R4. One in which the first two coordinates are non-zero and another in which the second and third coordinate are not zero. Then you can verify that u1 plus u2 is equal to the set of all x, y, z, 0 such that x, y, z belongs to R. Once again, u1 plus u2 is a strict subset of R4, that means the space in which u1 and u2 exist, and it contains u1 and u2. Thus, it is interesting.